Okay, so I'd like to welcome Dr. Ali Sanar. He's a professor of chemical engineering, and he's also the director of the Engineering Center for Diabetes Research and Education at the Illinois Institute of Technology. We are fortunate to have Dr. Sanar. He's, has a number of years of experience in this area and has some exciting new results in the design of artificial pancreas. He graduated, he got his PhD in chemical engineering at Texas A&M. He's a fellow of AICHE and a member of a number of organizations. He's published 2 books and over 180 technical papers in refereed journals and conference proceedings, and certainly an accomplished individual in terms of the body of research that he has produced. So with that, I'm going to go ahead and turn the screen sharing over to Dr. Sanar. And okay, so I've passed it over. If you want to start sharing your desktop, fantastic. We can see that.
Well, thank you for joining this webinar. And I will start by giving a brief background on on diabetes, because I know some of you have a very strong background in the area, but others may be just getting interested in this area. So I would like to give enough information to see where we are going with our activities in the development for the artificial pancreas. So we'll talk about diabetes, about glucose metabolism and diabetes, and then diabetes as a control problem with artificial pancreas systems, historical development of artificial pancreas systems, then sensors, monitors, insulin pumps, and then artificial pancreas control systems, followed by hypoglycemia early warning system, and then talk a little bit about multivariable artificial pancreas models and controllers. And then just a few slides about the future research directions will conclude the presentation. So diabetes is a metabolic disease in which the body either does not produce insulin, and that's type 1 diabetes, or the insulin production is at an inadequate level, and use of the insulin produced is not efficient, and that is type 2 diabetes. And type 2 over the years can also progress into type 1. And in terms of long-term complications, diabetes can cause cardiovascular diseases, kidney failure, neuropathy, retinopathy, and blindness. And in terms of short-term challenges, it can lead to dizziness, seizures, fainting, diabetic coma, and ultimately death. So this is a picture that was recently displayed in Wall Street Journal about 6 months ago. And you could see the countries where there is a large prevalence of diabetes. More than 12% would be Mexico and the Caribbean islands. The Middle East, Egypt, and Saudi Arabia are leading the pack, and Turkey is included in there, as well as Chile and parts of Canada. But if one wants to put in the number of people who have diabetes all in one country, the question would be, which country would that be? And when I usually ask the students, they either highball or lowball. They start with China and then they go to Russia. And I just say that they're both wrong because until the more recent set of statistics, it would have been the United States. With the latest statistics that have been made available, you can add to that now France. So The total number is about 380 million people, and of that, about 5 to 10% of it would be type 1 diabetes around the world. In the US, it's about 30 million people, and of the 30 million people, about 3 million adults and children have type 1 diabetes. So to recap, type 1 is the insulin-dependent one, where the body does not make any insulin, and every day, multiple times, the patient has to administer insulin either through injections or more continuously through an insulin pump. In type 2, the production capability of insulin is reduced, and also the efficiency of insulin use is reduced, and the treatments are different. Insulin is not the first line of defense in this particular case, but oral medications, exercise and diet and lifestyle changes are more the first line of defense. And the challenge for all of us is that the type 2 that used to be a disease that is diagnosed in the 50s, when people are in their 50s, now is creeping down to the teen years. So there's a much larger percentage of people who have type 2 diabetes at younger ages right now. The insulin administration can be done in one of several ways. The most prevalent one is multiple daily injections. The approach that's becoming more popular is the use of an insulin pump that can do continuous insulin infusion throughout the day and night. And there are also patch pumps, inhaled insulins, and there is also experimental work on developing some pills that will provide insulin through just taking pills as opposed to injections. The artificial pancreas system is a system that's duplicating the insulin production and secretion functions of the pancreas. This is actually a limited definition because there are other functions of the pancreas that affect also the management of blood glucose levels, and we'll talk a little bit about that later. But one thing that is critical is the use of the artificial pancreas increases the concern for hypoglycemia, namely very low blood sugar levels that may cause some dizziness, fainting, loss of rational thinking, and it can lead to diabetic coma and ultimately to death if not untreated. So if you look at the regulation of blood glucose, let's start with a stimulus like having some food that will increase the blood glucose concentration, and the increase in blood glucose concentration will generate some signals to the beta cells in the islets of LANGERHANS of the pancreas, and that will trigger some intercellular communication that would increase the secretion of insulin that's already depoted in the pancreas in these cells or islets, and also increase the synthesis of insulin. Then the insulin, when it's carried in the bloodstream, will go to muscle and fat cells throughout the body and will enable the uptake of glucose from the bloodstream into the cells, and hence, over time, reduce the blood glucose concentration. Similarly, the liver cells will also be getting the glucose, and they will stop synthesizing glucose from glycogen, but instead they will synthesize glycogen from the glucose that's coming in and cause reduction in the blood glucose level as well. So both of these will provide a negative feedback, and islets of Langerhans will stop producing insulin, and instead glucagon will be produced and released so that the uptake of glucose is stopped, and as the blood glucose level goes down, glycogen will also trigger the conversion of glycogen back to glucose for maintaining a steady value in glucose concentration. The blood glucose concentration for a healthy person is 80 to 90 milligrams per 100 milliliter of blood. With people with diabetes, it goes to a higher level, 110 to 140. And right after a meal, for a healthy person, it goes to 120 to 140 range. But with people with diabetes, it can go very easily far higher than 200 milligrams. The key concern here is the functioning of brain cells. The brain cells are very finicky. They use only glucose for energy. So there has to be a certain amount of blood glucose so that they would be able to provide enough nutrition to brain cells for them to function properly. Otherwise, this hypoglycemia potential becomes a rather large probability and cause for concern. So the pancreas is this yellow organ that you see at the center of the picture, and you can see some cutouts for the islets of Langerhans within the pancreas, and then the acini in the pancreas as well. This is better visualization of the islet of Langerhans, where you have both beta cells that are secreting insulin and the alpha cells that are secreting glucagon. And this secretion in response to a major change in the glucose concentration is first a sharp increase that you see. That's the increase caused by insulin that was already depoted in the system. And then as that supply is depleted, there is production of insulin, but the secretion is going down for a while. And when there is enough insulin that is manufactured in the islets and secretion increases again, we will see this increase in the insulin concentration again. So if we now go to the artificial pancreas, it's basically a simple system. And assuming that we have the human body in here, there has to be a glucose measurement, and that measurement has to be compared with a reference value, and the difference should be fed to a controller, and that controller is feeding a signal to the pump that modifies the amount of insulin that would be infused to the body. But if we strip this further down, this is actually what the patients have been doing for years manually, except that when there was no glucose sensors that were able to measure and report glucose concentration frequently, they were doing it through some finger sticks and collecting some blood sample to measure the glucose a few times a day. And then the controller was really the patient himself or herself to figure out how much insulin to deliver. and that insulin was injected a few times a day. So that, in my mind, is the first artificial pancreas, because it is the human mind and actions that are doing what the pancreas was doing initially. But of course, that's just a simple starting point, and things have become a lot more complex after that. And in 1974, there were papers that reported some of the experiments done both with animals and with humans. Here you could see a case where a patient is receiving both insulin and dextrose as prescribed by the control algorithm. And this upper figure is the open loop glucose concentration with breakfast, lunch, supper, or snack, dinner, snack over a certain period. And then the closed loop version is down here. As you could see, not only the values of glucose have been pulled down from undesirably high levels, but also the change in the glucose concentration has been reduced significantly. And this black sequence is the insulin delivered, and then these lines down here are the various foods that have, or the equivalents of foods that have been given. So on the one hand, this system provided a very good illustration of the potential of the artificial pancreas system. On the other hand, the glucose concentration was from intravenous samples directly from the bloodstream. The injection of insulin was directly to the bloodstream, and even the food in the form of dextrose was given to the bloodstream if needed for compensating low values of blood glucose. So on the one hand, it shows that indeed the artificial pancreas system is something that could be realized with technology. On the other hand, it's also showing that with the way they have been able to do it in the 1970s, it is confined to a hospital room environment, and it cannot be ambulatory. So this is the equipment that was used, and if you look at the arm of the patient, you could gauge the size of the equipment at that time to achieve the system. Now, if we fast forward to 2013, here is the pump, and I will show you another pump in the next slide. And here is the control system and display system. And at the background, there is also the ability to remotely monitor what is going on with this particular patient. So this information is reflected back on the monitor as well. One critical contribution has been a plan that was proposed by the Juvenile Diabetes Research Foundation in 2006 with a six-stage or six-level development with 3 different generations of artificial pancreas. The first level was insulin shutoff, automated insulin shutoff with the pump if there is very low glucose that is measured. And that has become a commercial reality in 2013 with Medtronic providing such a pump commercially. The second stage is to have a predictive hypoglycemia as opposed to just the current measurement that indicates hypoglycemia, so that one can take precautions in advance. The third one is hyperglycemia alarm systems along with hypoglycemia. And then the next level is the automated closed loop for basal and hybrid with a manual mealtime or manual information at mealtime to assist boluses that would be given. The next level is the fully automated insulin in closed loop. And then the next level, the final level, as it was perceived about 8 years ago, was the multi-hormone closed loop system. And most of the academic and industrial research groups have focused on levels 2, 3, and 4, and there are very impressive results that have been reported and are being reported. In our group, we decided to focus directly on number 5, the fully automated insulin in closed loop. And then there is an ongoing debate on whether glucagon is necessary or not, but more and more with the availability of glucagons that are longer-term stable, this is becoming a direction that most people are favoring nowadays. So going back to the artificial pancreas concept, it's a glucose sensor, an insulin pump, and a control algorithm. And here is one of the earlier pumps that have been around. But now, if you think back about the very small size pump and the very small size monitor and controller, we are getting ready to move from the hospital room to everyday life. And in various countries around the world, nowadays there are some clinical studies that are being conducted for patients that are staying at home and are using the artificial pancreas systems for extended periods of time, anywhere from 1 week to a couple of months for clinical trials. And this is just one of these technologies that has assisted this switch. This screen that you see is the screen of a smartphone, an Android phone, and this is a product that was developed at the University of Virginia, and Patrick Keith-Hines was the key developer with a lot of input from various researchers at University of Virginia. And it's a very simple system in terms of the display because it has green, yellow, and red light for closed loop, for the pump, or for the CGM actually to show about the glucose levels. And one can do remote monitoring as well. And then there is a rather detailed menu to select different options and screens. These are some of the other screens that they have available in their device for meals, for various plots of glucose and insulin levels. And you could see that in this particular case, there is a hypopotential that has increased, so now we have a yellow light here as opposed to the green light. As far as sensors are concerned, this is one of the areas where there is some weakness, but many industrial companies as well as startups and university labs are working on better sensors that will have higher precisions and accuracies, more reliability, and also longer lives. And in fact, there are some systems at university labs that can be used up to a year or more without any replacement and with only a few calibrations during the actual use. So we want sensors that are accurate and precise, reliable, and sensors that would not be affected by the presence of other substances in the environment where the sensor is operating. And the size of a sensor, if you look at this tip and the tip compared to the size of the hand, will give you an idea about the size of the sensors that are inserted under the skin. And this white portion is just a transmitter that connects wirelessly either to a continuous glucose monitoring system, or, as we will see later, to a pump directly. And just for illustrative purposes, I have used some of the pictures from the Medtronic site, but there are several other companies that have sensors and monitoring systems as well that are currently being marketed. So one of the questions would be, what else should be measured? And one way to start that conversation is to look at this curve. IOB stands for insulin on board, and it shows how much insulin on board is available for people who have different metabolic characteristics, and also depending on the type of insulin used, the survival of this insulin in the body will increase. And if you look at having maybe half of that insulin still available after 4 hours for a person that has very low dissipation rate of insulin, you could forecast the danger of giving too much insulin and causing hypoglycemia down the road. Unfortunately, there are no insulin sensors that are available to give information about the insulin concentration in the bloodstream. So that's a major weakness in developing the control algorithms. What we have done is to move in a different direction. We thought that there are several other metabolites in the body that are indicating a number of changes that are taking place in the body. And these may be caused by physical activity, they may be caused by sleep, they may be caused by other events that are taking place. And ultimately, the effect of all these show up in the blood glucose, but they show up with some delay. So we were interested in looking at the opportunity of capturing these changes as they are happening, as opposed to capturing the effect of those changes in the bloodstream using the blood glucose monitors. And we used this body media Sensewear armband, which has been in the market for over 10 years. Now there are quite a few other companies like Nike, Jawbone, Fitbit, Polar, and then a number of others. But this is probably one that has a higher accuracy and better list of signals that are available. So it measures the skin temperature, near body temperature, accelerations in 2 dimensions now. The more current versions have three directional accelerometers, heat flux, and galvanic skin response. And then using all these variables and their software, one can generate information about energy expenditure, the state of sleep, or the intensity of physical activity. So we have incorporated that information in our control systems as additional sensors. The other piece is, of course, the insulin pump, and you see again a picture of a commercially available insulin pump that talks directly to the sensor. So now most of the functionality of the continuous glucose monitor has been introduced to the pump as well. So there is no need to have, for many of the patients, another device monitor. They use directly their pump to do the monitoring and the decision making. And if we add all these pieces together, then we start with a glucose sensor that provides a glucose concentration signal, and we could use a computer or a smartphone as the control system. We need to provide the target glucose values or ranges. Then the amount of insulin that needs to be infused is computed by the control system and passed on to the pump that will infuse the appropriate amount of insulin to the body. And in various environments, both at home, in diabetes camps, and under some limited free living conditions with routine activities and low-level physical activities, these systems have done a very good job in regulating the blood glucose concentrations. So if we look at the control philosophies, one approach, the first one that has been looked into was proportional integral derivative, the PID control. The second approach that has gained a lot of traction is model-based control systems. Model predictive control has been one way. Adaptive control has been also another option that some people considered, but it's nowhere near the popularity of model predictive control. There is also now some robust control approaches that are being introduced, and the third kind is rule-based control systems. MD logic is one that is the most popular one, and it is the combination of some fuzzy logic and rule-based, knowledge-based systems to make decisions that mimic what a medical doctor would do in evaluating the conditions of a patient and subscribing the appropriate dose of insulin to be infused. And then there are some other control systems, including neural networks, bio-inspired control systems that have been presented in various meetings. For the PID control systems, Gary Steele has been one of the early proponents of this approach, and over the years he was able to add quite a few bells and whistles to this simple PID loop with estimators, with some constraints, and he has systems that are working pretty well to regulate the glucose concentrations of patients. In the MD logic, rules are suggested by medical experts, and then some of the constants or parameters are fuzzified, and then rule bases have been developed for various clusters of decision making depending on the activities of the patient, the types of food, and so on. And as more knowledge is acquired, these rules can be easily modified. But the challenge here is, as the number of rules increase, there is a need for conflict resolution, because some of those rules may give some action commands that are conflicting with other rules that are firing and giving action commands as well. So there is probably down the road a concern for this conflict resolution component with the fuzzy logic systems. In the case of model predictive control systems, if you look at the key components, the prediction model, cost function, constraints, and dynamic optimization, the model-based control system is an excellent candidate for regulating the blood glucose levels. And the prediction model is usually fixed. The target glucose, either as a value or as a range, is provided. And then some finger sticks are made to provide calibration values for the glucose monitor or the sensor. And then there are a number of disturbances like meals, physical activity, or stress. And these definitely affect the behavior of the patient. And some of them, especially the meals, have been introduced as feed-forward action to the model-based system as well. And the objective function will have a number of constraints and a good number of parameters that could be adjusted, starting with the prediction and control horizon to various weights. And the target glucose concentration could either be a reference value or it could be a range. And of course, the traditional approach is that we are trying to minimize the deviation from the target trajectory by using the least amount of insulin by minimizing this cost function. This is just a 30-second refresher for model predictive control based on the future values of the insulin infusion rates. One can predict using the model the future glucose values and look at the errors. And if these errors are more than acceptable, then one can go back and prescribe another set of control actions, compute the new future glucose profile, check the errors, and ultimately optimize this sequence of control signals and implement only the first one to repeat the same thing again at the next sampling time. So as far as the models are concerned, initially people started with detailed space models, and the parameters were often computed by using patient data. But more recently, there has been research results reported for by using simpler models, transfer functions that are third-order transfer functions generated from patient data with some individualized parameters, but many fewer parameters compared to the state-space model to act as the model for the model predictive control or for the H-infinity type robust control system design. Also, we should emphasize that control could be either to specific target value or to a range by reasoning that as long as the concentration is limited to remain within a certain range, then there may not be a need for making too many interventions in the insulin infusion rate. The last thing that's worth thinking about is the asymmetric risk for hyperglycemia and hypoglycemia, since hypoglycemia has more severe conclusions in the short term. The risk factor and hence the weights in the control algorithms should be adjusted accordingly in order to minimize the risk for hypoglycemia and not give too much insulin to the patient that needs to be combated later either by consumption of additional food or with some glucagon. In our research, we have decided to take a different direction. And the rationale for that is this patient data. It's data from a patient in 3 consecutive days. And one can see that the patterns don't match from one day to the next. So we thought that having a fixed model would not be necessarily a very good way to approach this problem. And we decided to build recursive time series models or their conversion to state-space form, update model parameters with new data every time data are received from the patient. And we have also added the stability assessment capability. In fact, later on, we converted that to a set of constraints so that as the model is being developed, we have some constraints that will force the system to be a stable model. And then we use this model using in a model-based control approach using generalized predictive control to compute the optimal insulin infusion rates. And just like in the case of model predictive control, use only the first one of the insulin values and repeat the optimization as new data are being received. So the time series model is going to have the previous CGM readings and as inputs infuse insulin flow rate, energy expenditure, and galvanic skin response. Both of these turned out to be the most informative variables from the Armband in improving the prediction of the glucose values. So we have kept them in model development. And then we have added the error between the estimated and measured CGM readings to provide the moving average component of autoregressive moving average model with external variables. Of course, all these parameters are updated recursively with each new measurement set that's coming from the patient. And the difference here is that going back to this general layout of the model predictive control system, now we have no manual inputs provided, and the model is expected to take care of representing the changes that are being taking place in the patient's body, and then the prediction model is recursively updated. Why go to multivariable AP to revisit the problem when people exercise? The sensitivity to insulin increases, and also more glucose is used for energy during exercise, and these two factors create a potential for hypoglycemia during and after exercise, and it may last not in terms of minutes, but in terms of hours, or on occasion, it can go for 24 hours or more as a potential. And to make matters worse, this is correct for low intensity and medium intensity exercise, but with high intensity exercise, things change, and there is a potential to go to hyperglycemia as opposed to hypoglycemia. And when that happens and the patient gives additional insulin to get rid of the hyper, it may also set himself or herself up for a hypoglycemia episode down the road. Another factor is sleep. Again, during sleep, insulin sensitivity increases, and the challenge there is, of course, the patient is sleeping, so he or she may not be aware of this low glucose state, and that might create some challenges. So to take into account all these factors, we thought that these additional signals would be valuable. And now you could see the armband in more detail with the sensors that it has on its surface. And this one is a version that can download data as a batch, so we had to do a lot of manual work to collect data at high frequency while it is operating in a batch mode. But it has given us valuable information both for modeling and for control purposes. And again, energy expenditure and galvanic skin response are the two variables that we have used. So in terms of the details of the model, we have this multivariable time series model that's being used, auto-regressive moving average with exogenous inputs, and there is a need to estimate the delays in some of the inputs or the effects of these inputs on the glucose concentrations. And I'm going to skip these equations rather quickly, since you have a chance to find them later, either in the papers or in the YouTube video of the system. And for the generalized predictive control, the objective function is quite similar to what we have already seen with the model predictive controller. And we have a number of constraints on the minimum, maximum insulin. We also have some on the rate of change of insulin as well. So now our multivariable AP has moved into something that has physiological variable signals as a feed-forward action and glucose signal as a feedback action going to the control system. And this is one of the results from clinical studies. And what I would like to show in here is that the energy expenditure when that person was exercising shows a significant change. And because of the energy expenditure signal, we are able to put together in the controller some additional logic that says that if that person is exercising, then go easy on the insulin infusion, so that while the glucose value is high enough over the range that we see as a desirable range, the amount of insulin that's being infused is dropped very quickly in order to prevent potential for hypoglycemia at a later stage. And here you could see that it just levels down in a nice way with just a small amount of carbohydrate that's given as a snack, and there is no hypoglycemia in this particular case. We have added the hypoglycemia early warning system to this so that we would have an additional level of security. Traditionally, the hypoglycemia early warning systems were based on trends, but we have preferred an alternative since we had these dynamic and subject-specific models that we were generating for our control system. We decided to use them for predicting the hypoglycemia potential of the patient. And this gives a certain logic sequence depending on whether the person is sleeping or exercising or doing routine daily activities, for issuing either early alarms or generating immediate hypoglycemia alarms. And we have tested the system first with data that have been already collected. And here, this is retrospective analysis of the data. So first of all, you see the raw data in blue, then the 6-step ahead prediction in red, and then the early alarm is given in green stars. And notice that starting that time instant, which is about 35 minutes in advance of the actual hypoglycemia episode, the system is beginning to give alarms that this patient will go to a hypo episode. And indeed, the patient goes to hypo, then comes out of it, and then we give early alarms again, and indeed, the patient goes to another hypo episode, and the same thing is repeated on every occasion. There are very few missed and false alarms, and this system was then added to our controller with direct information provided to the subject or to the patient for having some rescue food that would be about 10 to 15 grams of carbohydrate, granola bar or a glass of fruit juice was all that was needed. So this is the current version of our integrated multivariable control system. And again, with another patient, the situation is similar. One can see that, first of all, because there was very quick drops in glucose concentration, there were some triggers for having orange juice given to the patient. And then this is the episode where there is exercise, and even though the blood glucose level was very high, the insulin level was cut down, and indeed after that the blood glucose level came down to the acceptable range rather quickly. The experiments that we designed were open loop on the first day just to get a comparison basis. We didn't use this information to do our closed loop work. On the second day, the loop was closed. The meals were the same as the first day, as well as the exercise. And on the third day, again, the meals were the same as the second day, as well as the exercise, though the timing of the exercise may have changed. And data are sent to the controller and to the warning system every 10 minutes. And the insulin infusion rate is implemented after medical staff approval, and the time of exercise changes, and the finger stick is used when there is early warning for hypo, as well as giving a snack. And then snacks at other times are given only at prescribed specific times or when hypoglycemia is predicted. So the summary information that one can take out of this table is, with about 15 patients that were doing open loop studies just to increase our pool, we had severe hypoglycemia. The glucose concentration was less than 55. We had also hypoglycemia where the glucose concentration was in the range of 55 to 70. And then in the normal range, and hyperglycemia and severe hyperglycemia was also observed. But the critical factor that we're focusing on was the hypoglycemia. When we used our multivariable closed-loop system with 6 patients, and all those 6 are included in the cases up here. These were just patient 6 and patient 13 to give you an idea about the worst cases. But here all of the severe hypoglycemia are eliminated. There are a few cases with mild hypoglycemia, but very short durations of time. These are the durations of time during, or the percentage of the time during the whole closed-loop experiment. And with the integrated system, which were the last 3 patients only, there is no hypoglycemia of any kind that was captured in our data sets. So going to the future now, as engineers start paying more and more attention to this problem, the concepts of fault detection, diagnosis, risk mitigation became one of the key focus areas. Of course, we would like this optimal glycemic state where the patient has blood glucose levels in the range of, say, 110 to 130 all the time. But we know that in real life, especially with patients who are doing a lot of activities and changing their meal times, meal contents, the normal glycemic range of 100 to 180 would be desirable. But then things start getting more dangerous. There could be hypo or hyperglycemic states of the user. And these can be caused by the patient's behavior directly, or there could be some short duration malfunctions in the system, like temporary increase in signal noise or occlusion that's formed under the skin with insulin that is building into a depot but not being distributed in the body, or pressure-induced sensor attenuation, which happens when people who are sleeping would turn over and put the pressure on the sensor and that whole area where the sensor is located, which affects, unfortunately, the sensor reading. And then things may get even worse, where there may be specific faults in various components of the artificial pancreas, sensor, pump, control algorithm itself, and worst case would, of course, be the total loss of functionality of the artificial pancreas because of a breakdown. So one needs to develop some systems that will be able to combat this list of potential failures in sensors, in insulin pumps, in control algorithms, or in patient or human errors that has been listed by FDA as a representative sample. This is certainly not an all-inclusive list. And our approach to this risk mitigation by fault detection and diagnosis was first to interrogate data to see whether there is an abnormal situation or not. If there is no abnormal situation, then there is no additional work to be done. We just wait for the next data set. If there is an abnormal situation, so this is the monitoring stage, then one needs to divide and rule by looking at different problems. Is the controller functioning properly? The control logic may have some errors in it, or the control parameters may not be appropriate for the current state of the patient. Similarly, there could be some equipment problems, the traditional fault detection. There could be some signal transmission problems because of interference to wireless signals. And there could be problems in the interface of the equipment with the body, whether sensor or pump-related problems. So with all of that, there has to be a fault detection and diagnosis. And this can fit in with what we have as another module that will collect this information, do additional work, and provide some feedback to the system for doing activities such as use of estimates as opposed to actual values, filtering of data, retuning of the control system over time. And with that, we could lead to the next level, which would be the fault-tolerant control, where fault detection and diagnosis will feed into fault-tolerant control modules, along with the analytical sensor redundancy that will provide additional information, and if need be, controller retuning if the culprit is the controller, to provide a better control system for use and make this transparent to the patient. Similar activities can also take place with exercise-related challenges, but because of time, I prefer to stop here and just put these conclusions, which are first that multivariable adaptive artificial pancreas control without any meal or exercise announcement provides an easy-to-use system that may be more in demand with especially the younger generation of physically active patients with type 1 diabetes. And use of adaptive system identification and leveraging of the physiological information can lead to better glucose regulation. And integration of hypoglycemia early alarm system and controller can achieve hypoglycemia prevention during exercise and sleep, and risk mitigation, and ultimately fault-tolerant control and accommodation of physical activity effects are necessary in developing the next generation of AP systems, especially when these systems will become candidates for public use by a large number of people that would be interested in the more advanced technologies. To close, I would like to acknowledge some of my partners at University of Chicago, University of Illinois in Chicago, and at IIT, the students who are doing most of this work. And I would like to also acknowledge the funding and support of JDRF and NIH that enabled the continuation of our research work. Thank you, and I will be happy to answer any questions that you may have.
Fantastic. Well, thank you so much, Ed. That was a fantastic overview and also some exciting research results that you have. We have maybe time for one or two questions. I know we're really low on time right now. So any questions from the audience, you're welcome to put those into the chat window, or go ahead and unmute your microphone and ask Dr. Sinar.
Let me also put my email address in case you have questions that come to your mind at a later stage. Feel free to send me an email.
Okay, well, fantastic. Well, just in the interest of time, let me go ahead and just conclude then. And thank you so much for your presentation. Again, I thought it was very well done. So we'll go ahead and conclude now, and I'll post a copy of the presentation online, and that'll be available later today. So thank you so much, everybody, for joining.
And thank you for listening.